Oh, is it starting? Okay, cool. Yeah, hi. So I'm Elon. I'm a PhD student at MIT right now. I've been working on like different types of machine learning tools for intelligent robot systems. And today I'll present some work on that we did a while back on like planning with diffusion for flexible behavior synthesis. And again, if you have any questions or anything, you can just feel free to ask me during the presentation. Uh, so yeah, let's get started. So the title of this paper I'm going to present is called Planning with Diffusion for Flexible Behavior Synthesis. And this paper is kind of inspired by this idea that like normally a very like nice approach towards like doing RL as well as data-driven control is to basically take a data set of transitions. So these are states, actions, state pairs, as well as a reward function, and maybe the current state S naught. And then basically what you can do is you can train a model that models the dynamics of the world. So it just basically, given the current state in action, it predicts the subsequent state st+1. And then once you have this model, what you can do is you can then evaluate many different plans, a naught through at, and select the one that like has the highest reward under your learned reward function. And you can basically just recursively apply this dynamics model a very large number of times. Well, this like sounds really nice because this sounds like a very nice approach towards doing RL, as well as just like this data-driven control, because you can just learn the predictive model through supervised learning by just supervising the dynamics model to predict the data set of states. And it's also very nice because then once you have this model, you can basically run optimization on the actions to choose the set of actions that maximizes the reward under this dynamics model. So in principle, this is a very nice way to do RL, because when you actually do RL by like just doing dynamic programming or something like this, it ends up being a bit unstable because you don't have ground truth values, and a lot of the bootstrapping becomes cascades errors. So like this idea of using trajectory optimization with neural networks is great in principle, but actually in practice, it's a bit of a headache. And the reason why is because when you unroll this model multiple different time steps in the future, the actual state predictions in the network become unreliable over time. So the network gradually becomes out of distribution. And then if you like optimize for rewards with a neural network, it produces a series of like somewhat like adversarial examples in the trajectory space of the neural network. So essentially these trajectories that you optimize for might appear to the neural network to have very high reward, but in practice, it doesn't really work because the actual rewards end up being poor. And the thought is maybe it's because neural networks just aren't that great. But really, this is probably not the case, because we know that neural networks, when you like apply it in the settings of like generative modeling, for example, on images, they can generate very like complex and very like amazing images. So the question is, and the question we really want to explore in this paper is whether we can use these advantages in generative modeling to basically learn effective RL agents. And what we do is we basically propose a framework where we can change planning into a generative modeling problem, where we basically try to like offload as much of the reward optimization and dynamics rollouts I was talking about earlier into a generative modeling procedure. So recall that previously what we did is we trained a predictive model, which tried to predict what the future states are given the current action, as well as a reward function that basically evaluates a trajectory that you generate. And what we do is we now replace this predictive model with a giant generative model. So in particular, we use a diffusion model, but like that's not the biggest detail. I think the biggest detail is that we basically learn a single generative model to model the entire trajectory. And then we basically replace the prediction and planning problem as basically inference on this big generative model, where you basically, once we've learned this generative model on this set of transitions from the data set, we essentially use the reward function to bias sampling under the generative model to construct plans in the world. So this essentially replaces this entire block with a generative model, like where we learn a probabilistic model across trajectories in your data. And then we basically use conditional inference to infer trajectories that have high desired reward. And what we do is basically, this is a bit more on the implementation side, but we can basically represent trajectories kind of like one-dimensional, say a single channel images. So you can imagine that on one hand, you have the planning horizon, and then on the other hand, you have the state and action dimension. And then basically this, you can view a trajectory as a 2D image. And what you can do is we can train a diffusion model, which we call diffuser, to basically model this probability distribution by gradually denoising and going from random noise trajectories into a trajectory that represents individual states and actions. And we essentially use, and we'll talk a bit about it later, we use these 1D convolutions to like maintain this idea of temporal equivariance and horizon independence. That's very nice when you have single step dynamics models.
Can I ask a question?
Yeah, sure.
So just to make sure I understand correctly, what you try to do with this work is that given us a bunch of trajectories, so state and action pairs, you want to learn the distribution of these trajectories with a generative model that can then learn to generate distributions belonging to the correct distribution. And then you want to train model-based reinforcement learning agents, right? On these trajectories to learn the reward.
So that's not quite right, I guess. So if we going back here, so essentially, so normally, so I guess this is like, or I guess the instantiation of model-based reinforcement learning is basically you learn a single step dynamics model, and then you basically can run like, so there's no learning really in the model-based RL portion. You just basically run optimization over the actions to get a high reward goal. So what we do is we replace the single step dynamics with like a full level trajectory generative model. So it like models the entire trajectory. And then in this setting, then we do inference. So we don't do any learning again. We just do inference on the trajectory model to find something that has high reward. Does that make sense?
Yeah.
Yeah. Cool. Yeah. Feel free to let me know. Are there any other questions?
Yeah, I have a question. The question is actually in terms of the implementation. For the implementation, you said that you manage the image, so the pair of the states and the actions as an image, but then at the bottom part after the diffuser, these are at the state where it's fully noise, or what is this transition for?
Sorry, I'm not quite sure. So basically, we represent this as basically a trajectory where you have a set of states as one like dimension of your image, and then you have the set of, actually, let me see. Yeah. So basically, you have your planning horizon is one dimension of the image, and the state dimension plus action dimension is a second dimension of your image. And so basically, at the end, when you finish prediction here, what you have is you'll get this like 2D grid. And then like if you want to see the action and state you should execute on time step 3, you can just look up the value here in the image. Does that make sense?
So basically what I don't get is so at the top you have the sample from the so these are the samples that you have or the samples that you use from the diffusion process?
So essentially we initialized the diffusion process was like Gaussian noise, right? And this is the final output of the diffusion process. So this is this is just random noise at the beginning. So basically so the output is your plan.
Okay. Yeah. Great.
Okay, great. Cool. Are there any other questions? Okay, cool. Yeah, I will go on. Yeah. So basically we essentially like the diffusion process starts from Gaussian noise and it basically generates a plan. And this is a bit different than existing works because typically people like do prediction as a autoregressive procedure where you like predict one state after another. But in our setting, it's a non-autoregressive prediction procedure. So the entire trajectory is predicted simultaneously. So you can imagine that you start with like some clean trajectory here, like maybe this is how you want to move this robotic gripper to grip this block. And what happens is like we basically like you add Gaussian noise to it, so you become this like gaseous set of particles. And our diffusion process basically learns to go from this Gaussian noise to construct this plan, right, by running many steps of this sampling procedure. And you basically, after running many steps, you can basically go from this very like noisy like set of states and actions to this clean trajectory that you can actually execute. Okay, so when we do this, so when we change our dynamics prediction to be non-autoregressive in nature, it no longer becomes it's no longer Markovian. So what does that mean? So normally when people learn a Markov dynamics model, you essentially just model the evolution of one state after one action. So in that case, if you have trajectories like this and you have trajectories like this, then you can. It's easy for the Markov decision process to model trajectories that like go in a kink, or because like essentially these are each local transition is valid. So since the Markov decision process just models single time step transitions, it can basically model these trajectories. But if we just model trajectory level trajectories, the issue is that then if we only model these trajectories and we only model these trajectories here, then we can't really generate trajectories that are novel combinations of these two trajectories like this. And the reason, and it's just because we don't have data, because we're just training this trajectory as a single data point. So we get around this issue by using this idea of temporal convolutions. So what we do is we formulate prediction by using using these like local windows. So when we're doing this denoising process, essentially a filter just attends to a local region inside this trajectory. And when you only attend, since each like convolutional filter just attends to a very local patch of this trajectory, you can imagine that the denoising process is kind of local in nature. So when you try to like predict the value of this data point, or like predict the value of this data point, you basically only look at these local values. So this enables our approach to generate trajectories that like can be novel combinations of your input trajectories. So it can be these kinks. And here's basically a visual procedure of how this works. So you basically start from a set of like so you start from a set of like these very noisy like states and actions, and as you run the diffusion procedure, eventually you converge this image, and then you can convert this image to like this robot state space. So you get these plans. And another nice thing about this is, as I mentioned before, the prediction process is done using these like local conv layers. You can like local temporal conv layers. So you can just input a longer like noise trajectory vector into the diffuser model, and then you can create longer plans. Okay, cool. So this is like a middle segue. So I'll now talk a bit about like using these models to compose different, like actually planning with these models by composing different probability distributions. But like at this point, if people have any questions about how you can actually generate trajectories using this generative procedure, you can feel free to ask now.
Yeah, I have a question about the last slide here. When you mentioned that you can generate longer trajectories than what you trained on, right? How does that work with the, let's say, distribution of longer trajectories? Does it keep generating a trajectory that is like basically that follows the same distribution of the shorter trajectories, or does it account for a different distribution for the longer part?
Yeah, so for the longer part, it would follow the distribution of the shorter part. So I guess if you look at it from a probability point of view, we're just decomposing the P of trajectory into a bunch of local patches. So essentially, our comms are like basically decomposing P of tau into like P of like tau 1 to 5 maybe times P of tau 2 to 6. So basically, we're decomposing the likelihood of a trajectory into these overlapping patches. So when you have a longer trajectory, it's still like you can still model that probability distribution because you've like decomposed it into many different overlapping subpatches.
Okay.
I have another question in terms of the implementation for the non-Markovian. Is it are you using the same approach as the DDIM paper?
So not really. So what the DDIM paper is talking about is this idea that you can do faster inference on diffusion models by basically treating them like okay. So yeah. So both use this idea like a Markov process in a sense. But what DDIM is doing is in your denoising process, you can just treat it as a Markov train, and you can use this to like basically jump past multiple steps to diffusion. What we're doing here is like independent of sampling. What we are saying is like how can we model different variable lengths of trajectories, or how can we model trajectories that are novel combinations of the ones we've seen before?
Yeah. Okay, but then the sampling process is because what it is confusing is that you said that this sampling process is non-autoregressive. So I was thinking that the implementation of the sampling, it has to be related somehow with the normal coding approach to the sampling process of the DDIM paper. But yeah, because you said that it's non-autoregressive, so then I was thinking then. Yeah,
oh, I see. So okay, so here's the I think here's maybe the confusing thing. So when we say prediction is non-autoregressive, what we mean is normally so this is not in the diffusion context. Normally when people do like prediction, right? Like you do like you predict current state S0, then you predict the next state S1 and S2. So you basically predict each state one by one. What we do instead is we predict all the states at once. This is what we mean by non-autoregressive. Yeah, so the diffusion is a completely separate thing.
All right, so and then for sampling, I guess you're using the classical sampler.
Yeah, we just use DDPM to sample. And you could use any sampler really. All we're saying here is that we want a generative model that can model the trajectories.
Right. Yeah. Thanks.
Okay, great. So the earlier portion I was talking about how we can use diffusion models to model generative models of trajectories. So the next portion, I'll talk a bit about how now if you have a generative model that's captured by a diffusion model, how you can plan with it. And the general idea is that you can synthesize different behaviors using a learned generative model by just composing it with different function or different other probability distributions, which kind of like guide the distribution you can imagine. So imagine that like I have my trajectory distribution p theta tau, which is the learned diffusion model over trajectories I was talking about before. I can learn or construct a separate model h tau, which basically specifies the types of trajectories I would like. And then if I multiply these two distributions together, I'll sample trajectories that are high likelihood under the original trajectories in the data set, but also which exhibit the a particular aspect I would like. So here we can, so the diffusion model essentially models like, it can model all of these like 2D paths essentially. And then your guidance function can be some type of value function. So essentially the guidance function says you should preferentially stay in states in this area as well as states in this particular area. So it basically assigns high likelihood to to trajectories which have many states in this red area, and low likelihood to all trajectories which have states in this blue area. So if you multiply these two distributions together, then you can basically get a new distribution. And if you sample from that new distribution, you can get behaviors that on one hand kind of look like the behaviors you've seen originally from the diffusion model, but at the same time also exhibit the particular characteristics you want to specify. So essentially this idea of composing diffusion models with additional distributions gives that you specify and gives you a way to flexibly plan with them. And this type of guidance function can transform unconditional diffusion or trajectory model into various different types of conditional policies for a very large number of different tasks. So the first one we can talk is this idea that you can turn this diffusion model into an offline reinforcement learning model. So you basically train this diffusion model on a series of different trajectories from S0 to S6. And what you can do is you can then train a separate reward function that basically just sums up the rewards at S0, S1, all the way to S5. And you can just essentially multiply these two distributions to get a new distribution, p theta tilde tau. And then and it turns out that when you sample from the diffusion model, this essentially just corresponds to adding the gradients of the diffusion process plus this guidance function. And this enables us to, and one nice thing about this factorization is you can imagine that dependent on the reward function you want to optimize, you can learn a single diffusion model p theta tau and use various different types of guidance functions for different as different rewards for different tasks. And what we find is that this approach enables us to perform very competitively with a variety of different offline reinforcement learning techniques, including ones that are specially designed for offline reinforcement learning. Without any we just use the unconditional generative model and we just adapt it to the problem on hand. But again, it's not super exciting that we can do things that are very similar to what people have been able to do in the past. What I'll talk about next is how this is really just one thing you can do with this approach. You can do a lot of other things that can be much better than what people have done in the past. So another thing you can do is you can actually use this to specifically specify planning in a trajectory. So what you can do is you can, again, take this unconditional distribution over trajectories that you constructed, and you can compose it with a Dirac delta distribution. So this guidance function just says, I have as probability 1 that have probability 1 as long as your trajectory has a particular start state and a particular go state. And your probability is 0 if it does not have your start and go state. And if you compose these two distributions together, again, you get this modified distribution p theta tilde that can basically generate plans from a particular start state to go state. And this is really easy, again, to integrate into the diffusion sampling process because you basically at each step of denoising, you just fix the start and go state. And it turns out that I've also been working a while on the different separate class of generative models called energy-based models. And those and both diffusion and energy-based models have very natural methods to do this type of composition of probability distributions. But this essentially allows you to construct a goal-seeking policy at test time. So if I want to construct a policy that goes to a new goal at test time, all I need to do is just change my sampling procedure to have a particular new state. And now I have a policy to that particular goal. And we find that this is pretty effective. So here we show the, 3 different environments. So this latter environment is a very long planning problem. So it has 512 states. And what you can do is just by specifying the start state and the go state, and then running this inference procedure, you can basically get a plan that goes from the start state to this go state. And these are just randomly specified at test time. So I could take any 2 locations in this maze and would be able to get this goal.
Ideally, you could add also more intermediate steps, right? So you could have a very, let's say, specific path.
Yeah, exactly. Yeah. So you can also add different waypoints. So you can add a waypoint here, waypoint here. This really allows you to very controllably generate a plan to particular goals. Yeah, and we find that traditionally this is a very hard problem for offline reinforcement learning or offline decision making approaches, because they rely on this concept of rewards, which is really sparse, especially in these long horizon maze environments. But if you just learn these generative models over trajectories, it actually performs very, very well on these maze 2D tasks. And you can see that both in when you try to evaluate a particular start and go pair, as well as when you evaluate on novel, any start and go pair. And I think even more, a thing that is even more exciting to me is this idea that you can just use this to specify arbitrary costs on a trajectory. So you can imagine that this is a probabilistic version of trajectory optimization. So what do I mean by this? So you can, again, take your unconditional diffusion model, p theta tau, which models a generative model across these states and actions. And what you can do is you can compose it with a separate guidance function that basically just assigns costs to particular states. So it basically, you just sum up these cost functions at per state. And this cost function can say, oh, are these states in this forbidden region, or are they in a physically valid region? Are they exhibiting a particular gate you want? Are they going to a particular goal? So these cost functions are just any user-defined cost function. They can also be learned. Of course, they can also be learned, but it's basically, it just gives you a very flexible way. These cost functions can specify any type of behavior you want in your trajectory. And what you can do is, again, you can basically just compose these 2 distributions together, and you get this novel distribution that like basically optimizes the cost you will specify. And yeah, basically, like I said, it's a learned analog of trajectory optimization. And a task we evaluate this in is this this task of block stacking. So you want to stack these blocks into a block tower. And what you can do instead is you can now specify cost functions. So you can say, my first cost function specifies that this gray block is on top of this purple one. And the second one specifies that the purple one has to be on top of the red one. And the third one says the red needs to be on top of the blue. And what you can do is now when you do this, you can just like control your behavior. So you can control it to like basically stack this block in this particular configuration. And what's interesting is like in this setting, we use cost functions that we hand designed. While in the earlier settings, we used them that were learned. So like so this procedure both allows you to like specify hand design setting constraints as well as learned ones. And again, this is a really challenging problem for existing offline reinforcement learning benchmarks because it's very sparse reward and it's very long horizon. And also it requires these models to like kind of compositionally generalize. And so our approach in yellow is much better than prior approaches. So yeah, so that's a brief overview of our paper. Yeah, so I'm happy to take any questions about the paper now.
Right. Thanks for the presentation. I have a question that I don't know if it's relevant, but I was wondering, can you maybe use also this approach for shortest path planning, like for the TSP problem or similar?
Yeah, I think you could, right? So what you could do is you could like just train it on different like paths on the graph, and then you have a cost function that specifies like the cost of your current path. And then you can basically just use the sampling procedure to then try to solve shortest path.
Thanks.
Maybe, can you maybe explain more about how you introduce the notion of reward in the diffusion process?
Oh yeah, how do you introduce the concept of reward? Yeah, sure. So this reward function here, so what we do is we train on this offline reinforcement learning data set. So the offline reinforcement learning data set will have like in each state, it will be assigned a reward, like that state will have a reward, right? So what we do is we basically train a function that just takes the state and regresses reward. And then what you can do is now like in the like when the diffusion model is producing these intermediate states, right? You can just evaluate the reward function at these states, and then you can use that to like basically provide a gradient to refine the individual states.
Oh yeah, okay. Yeah, it's kind of the noise in posterior. Yeah.
Yeah. So I think I think that's pretty nice about like using diffusion models to do this type of conditional sampling is basically like each step of the diffusion process, you can use the gradient information from the data to basically guide it to do the different things.
Yeah. And did you also try like other new methods like for conditional guidance? Because there's a paper also was conditional guidance for distillation of diffusion models, something like that.
Yeah, I think all of those could definitely make all of this faster. I think the goal was like basically, so I think one thing is if you tried to use distillation with conditional guidance, like you kind of distill this conditioning into your model. So like it doesn't generalize as well at test time to new conditions, right? Because like you've only distilled a certain set of conditions into it. So I like this iterative process in diffusion models because I think it enables you to adapt to different constraints pretty easily. But yeah, I think we wrote this paper a while back, I think before diffusion models became popular, really. So like we were working on this like last July, not like last July, like 1.5 years ago, July. So at that time there weren't that many techniques to really do conditioning and stuff like this. I'm sure like nowadays was like the tons of papers that have come out in the last year. I'm sure there are better approaches to do like each of these steps. But I think that the thing that really attracted us to this is this idea that like you can use diffusion models to do like this type of probability composition. And I think like this type of like composing these probability distributions, like one trajectory level distribution and like one distribution that specifies the aspect of trajectory you want. I think that that is a pretty powerful tool for flexible behavior generation.
Because I think it's interesting to see, for example, this drawback in terms of the accuracy that you were talking about the plants, and in terms of the effect that the fast sampling has in the accuracy of the plants.
Sorry, say that again. I didn't quite catch that.
But yeah, so I was thinking that probably it's interesting to see what is the effect of introducing, rather than having the typical DDPM with versus fast samplers, because as you said, maybe,
oh, I see.
Yeah.
Yeah. So in some recent in some like if some follow-up collaborations I've been working with people, we have replaced the DDPM sampler with like DDIM, and it's quite a bit faster. So you can like, I think our setting, like I think we used 200 steps, although we might have reduced it to 40 later. But with DDIM, you can just use 10 steps of sampling. So it can be much faster. In terms of behavior, I do believe that when you make it faster, this like conditioning works less well also. So like there's a bit of a trade-off.
Yeah.
Can I ask something more about the reinforcement learning part?
Yeah.
So here you assume that you already know the reward, right, for each state when you impose the function h. But then if you go a couple of slides forward, right, like I guess at deployment you want to impose generic functions h, right? So how do you exactly specify new cost functions h to get the diffusion?
Yeah, so in this case, like imagine I'm an engineer, right? So I have like, or like maybe I have learned the diffusion model over like how to drive a car or something like this. And basically I have some other module that's told me a car is coming, I need to avoid that, right? So it's very easy for you to characterize avoid hitting this car or avoid hitting this obstacle, right? So like the H in this setting is basically we hand construct it. So like a lot of the times you know what you want to avoid, but you don't know what is a good like trajectory to synthesize, right? So in this case, we construct the H. But at the same time, you can also imagine that like maybe you have a data set. Maybe you said this type of behavior that you did is unsafe, and this type of behavior is safe. So you can train some type of classifier, and again, you can use a gradients of classifier to guide your diffusion process. So I think either could be good.
Okay, and again, in the training setup, which you mentioned is offline reinforcement learning, you assume to have a bunch of trajectories available, right, at train time with associated rewards.
Yeah, well, so I mean, like for these latter two settings, you don't need rewards because we don't even use the reward function to bias the model, but you always, you need a lot of data from the trajectory model, right? And I think a good question is how can you actually explore with these, like how do you use these models to explore in the environment, right? Like let's say you have no data. So the normal RL setting is you have no data and you need to gather the data to learn, right? How would you do it with this setting? It's a pretty interesting one.
Yeah, like do you, for example, if you have a simulator, do you move the agent at random, or do you follow some policy, some heuristic?
Yeah, I mean, like on one hand, what's interesting is like if you look at these RL algorithms that like people used to use in an online setting, they also don't really have a principled way to do acceleration. Like what you do is you just run like this dynamic programming procedure, and then like if the reward tells you how to explore, then you can then like the RL agent does explore a bit. But like also in our setting, if the reward tells you to explore, this combination of models will also tell you to explore. But the thing is, if the reward function isn't like beneficial for exploration, like let's say you have no feedback from the reward function, or the reward function just encourages you not to move, then the only way RL explores is by using like this epsilon greedy, where you like randomly choose an action every like 10 or 25% of the time. So you can imagine that with this like diffusion parameterization, you can do the exact same thing where you like every 25% of the time you just randomly explore.
Okay, but then you would get, and then this is probably like then you get a distribution of trajectories that are not necessarily good trajectories, right?
Well, so one thing that is that like this diffusion model here, right? It just needs to be
We lost you for a second.
Oh, hello. Can you hello?
He's getting back. Yeah. Try again.
1 second.
We lost him. Yes. Hello?
Hello. Hey, can you hear me now?
Yeah. Perfect.
Okay.
Yeah.
Yeah. Sorry. What were you asking earlier? I'm not sure. I think I got cut off.
That you learn just a generic probability over trajectories and not necessarily over optimal trajectories.
Yeah. So yeah, essentially, like, as long as this for guidance function like can capture good reward, right? So if it's a reward regressor or something like that, as long as that works, this just can just model all the trajectories. So it doesn't have to be perfect or like even good trajectories per se.
Okay, thanks. All right. Anyone else has questions? Bucho. We cannot hear you. A question? Okay.
Do you hear now?
Oh yeah.
Yes.
Okay.
Yes.
Perfect. Yeah, sorry. I was saying that I missed the beginning, so maybe you mentioned, but my question is, how does this scale to larger scale problems with bigger state space, for example?
Yeah, so we recently had this paper called like Learning Universal Policies through Text Conditioned Video Generation, which basically takes the same diffusion procedure but runs it on like videos on the internet. So like diffusion models have been shown to scale pretty well to both like very large images as well as very complex video settings. And we found that like if you apply this to a video setting, it also works pretty well.
So could you maybe summarize the biggest benefit of this method then?
Well, so I think the thing I like the most about this method is this idea that like you can basically use like different guidance functions to like adaptively plan or specify the behavior you want, right? So if you want your agent to optimize a particular reward function, you just put that in the guidance function, it can optimize it. If you wanted to optimize the cost, it can do that. If you ask it to reach a goal, it can do that. Like this gives you a very general purpose way to like construct behavior at test time on the fly. And then I think in addition to that, it just turns out that this approach also seems to scale pretty well. So you can use the same approach to like do very complicated like high dimensional videos and text. So that you could say is an added benefit.
Thank you.
Maybe one more question. Does this approach require full observability of the state, or to rephrase it, would it be applicable in partially observable environments?
Yeah, so I mean, we do just learn a probability distribution over states, right? So like whether the environment is partially observable or not, it would generally work. I think there are some like contrived settings you could say that you could argue that this doesn't work particularly, but in general, for most partially observable problems, right, the distribution over future states is still like probabilistic, right? So like this model can still model it. The only caveat is like the plan that's generated by this model, right? If you execute a single step, it might be good, but if you execute multiple steps in the future, it might be inaccurate, right? Because more information that you haven't seen before may like arise.
Mm-hmm. But you can use it stepwise eventually, this method that you have.
Yeah, but
right?
you can also you can just plan out each step, and then that should work well, I think.
Okay, so you could do some sort of MPC, model predictive control with the diffuser.
Yeah. I mean, the goal actually of the diffuser was. I mean, it actually looks very similar to MPC, right? Like you essentially just learn a model, you learn a model, and then like instead of like the MPC procedure, you use this diffusion sampling procedure as your MPC procedure. Yeah, like our goal is basically to use this as MPC. Like one thing I didn't talk much about this much is in MPCs, you like generate a set of plans, and then in the next time step, you basically warm start your plans using your previously generated plans, and then you run a couple more steps of MPC. We discuss it in the paper. You can also do the same type of flash planning with the diffusion process. You just initialize denoising using like the plan you generated from before. So like a different read of this paper is this is just a learned version of MPC or a learned version of model-based planning, essentially.
Okay. Yeah, Thanks. Any more questions? Okay, then thank you so much for the presentation.
Yeah,
And,
sure.
yeah, we maybe get in touch again by email later. Right?
Okay, great. Thank you.
Thank you so much.
Thanks.
Have a good day.
Have a good
Bye.
day.
Thanks a lot. Bye-bye.